In this example, we will integrate x to the fourth times e to the x. So looking at our integrand, we see it fits one of these desired forms for integration by parts, a polynomial multiplied by an exponential. Now, one thing to notice, because it has this x to the fourth power, we would have to apply integration by parts 4 times individually, which we certainly can do. But instead, what we're going to do is use this technique of multiple integration by parts introduced within this section. So kind of as a reminder, how we do this is we create a table. The first column of the table is going to have a sign, a plus or a minus. The second column is going to correspond to the function u, and the third column is going to correspond to dv. So we're going to let u be x to the fourth, and dv be e to the x. And notice, in order to fill in the table, I put the x to the fourth in the row underneath the u, but I put that e to the x in that top row with the dv. And what we do is we differentiate down the u column until we get back 0. So 4x cubed, 12x squared, 24x, 24, and 0. Then we, in the dv column, we anti-differentiate corresponding to dv. So the antiderivative is e to the x, e to the x, e to the x, e to the x, e to the x. And then in the sign column, we alternate with a plus, minus, plus, minus, plus, and when we get to the 0 in the u column, we stop. And when we apply this multiple integration by parts, we can just work our way across row to row. So in the first row, we have a plus sign, and what we'll do is multiply together the two functions. So we're going to have an x to the fourth, e to the x. Then we go to the second row, where we have a minus sign, and we multiply the two functions together. So minus 4x cubed, e to the x. And we just continue on in this process until we hit the stop. So that next row will have plus 12x squared, e to the x, then minus 24x, e to the x, and finally plus 24, e to the x. And because it's an indefinite integral, we also remember to add on our plus c.